Okay, let's do the second part of the fundamental theorem of calculus now. This is the part that allows us to evaluate integrals by finding an antiderivative. So let me state the theorem here. So if little f is integrable and say on the interval from a to b, and f is a function on a b such that f prime is equal to f for each x in AB. So let me say that's at x and at x. Then the integral from a to b of little f dx is equal to f at b minus f at a. Okay, so that's the fundamental theorem part 2. Let's see how this one's going to work with a picture. Alright, so let's get me a graph here. I want this to be sort of an increasing graph. We'll have it like this, and this is going to be capital F. Okay. So what we can do here is at A and here's at B, and I want to tie to this a function where the derivative, this is increasing, so my derivative is going to be positive. It starts out increasing kind of high, kind of fast, and it slows down in here, and then say this is little f, which is equal to f prime from A to B. Alright, so what we're doing is we're adding up pieces in the partition. So say here's xi and here's xi plus 1, right? And well, if I look at sort of a similar piece in here, and this is xi and xi plus 1, what I can do is I can see, well, the value of this versus the value of that. So that'd be capital F of xi plus 1 minus capital F of xi. That's going to be sort of how much this changes over this interval. And what I want to do is I want to associate that change to the area here. I'm adding up these areas as I move to the right, and so the change, this delta capital F value, should equal this area here, right? And this value divided by the delta xi, which is xi plus 1 minus xi, by the mean value theorem, that value has some point between xi and xi plus 1. There's some point in here, some c value, so that what we get is f at xi plus 1 minus f at xi equals f at c times xi plus 1 minus xi. That's the mean value theorem. Okay. And so this and this, if we add them up, So if I take the sum from I equals 0 to n minus 1, capital F of xi plus 1 minus capital F at xi, that should equal, adding up the same things, I'm going to call this ci for the c in the ith interval, 0 to n minus 1, f of ci delta xi, and this gives me a bound on the upper and lower, right? This is between mi is bigger than or equal to f of ci is bigger than or equal to little m I. So because of these two things being equal, I get that the upper with p capital or little f is bigger than or equal to this sum from I equals 0 to n minus 1 of f of xi plus 1 minus f of xi, and that's going to be bigger than or equal to the lower partition here. And so as I go over all partitions, this thing's always in the middle, so whatever this value equals, which this is a telescoping, I get u of p comma f is bigger than or equal to f at b minus f at a when I get that telescoping, and that's going to be bigger than or equal to L of f p. So this was true as long as I could use the mean value theorem, and our assumptions make the mean value theorem work, and in the limit then this goes to the integral from a to b of f dx is bigger than or equal to f of b minus f of a is bigger than or equal to, well, the integral from a to b f dx, so they have to be equal. Oops. Of f dx is equal to f of b minus f at a. Okay, that was most of the proof. The details throw an epsilon in there, and it sort of bounds this inequality that I've got boxed by taking the upper minus the lower is less than epsilon and that sort of thing. But the idea is now we take a limit of the thing in the box and I get the theorem. Okay, we'll call that good for the proof. Let's do a quick corollary. And this is integration by parts. So suppose f and g are differentiable on AB, and f prime and g prime are integrable okay, then the integral of capital F times g prime dx from a to b is going to be equal to f times g evaluated at a and b minus the integral from a to b f prime times g dx. Okay, and why is that? Well, let's use the fundamental theorem of calculus part 2 and look at f g and it has derivative f g prime plus f prime g. So, by the fundamental theorem of calculus part 2, the integral from a to b f g prime plus f prime g dx is equal to fg evaluated at a and b. Well, I can just break this into two pieces on the left, so I've got the integral from a to b fg prime dx equals fg evaluated at a and b minus integral f prime g dx at a and b. Okay, so that's the last of the integration stuff I want to actually prove. We'll go through and work a few exercises in the next couple days.